In the previous video, we extended the concept of conservative energy and showed that we can make it apply to cases when we have an interaction between two particles, both of which can move. So we have particle 1 and particle 2, which are acting on each other with some force. And we showed that we can define this force in terms of a potential, such that specifically the force F12, which depends on the difference in position between particle 1 and particle 2, that is vector r1 minus vector r2, that's equal to minus the gradient with respect to the position of particle 1 of some potential, which also then depends on the difference in position between the two particles. One thing that we didn't show, but that's relatively easy to demonstrate, is that if you have this formula, you can invert it and come up with the integral version of it, so that the potential that's associated with the two particles, this pair potential, u of r1 minus r2, can also be written as a path integral from some r0, which typically will be at infinity, to r1 of this force between the two particles that depends on the difference in position between the two of the particles, scalar dr1. And I've added primes here again, as usual, to distinguish the limits from the variable in the integration. So in this case, then the potential is just the energy that's required in order to take this particle in from infinity toward particle 2, which then would be stationary. Or you can define it equivalently, if you like, as minus the integral from r0 at infinity to r2 of f21 r1 minus r2 prime scalar dr2 prime. Okay. So if we've done this, it turns out that now we can really come up with a slightly different definition for conservative force compared to what we had before. So we still have two conditions. The first one now is that the force between the two particles depends only on position, but the position on both particles. And then the second condition is that if we move one particle, particle 1 for instance, around a closed loop, then we get a total work of 0. Okay, that's very similar to the old definitions of conservative force that we had for particles with external forces. We have only just extended it to the case of two particles interacting. Okay, so that's two particles. Of course, in a real system, you rarely have just two particles. You will have many. And that it seems that at first glance that things would be much more complicated, because if you have multiple particles, then each particle will interact with all the others, and you have many more forces, and it would seem that the expressions you'd need to work with are much more complicated. However, things are simple, relatively speaking, because even if you have many particles, each interaction between any pair of particles is associated with a single potential energy. So for instance, the interaction between particle 2 and particle 3, when we have this interaction pair here, and we can associate with this interaction pair some potential, right? So we have interaction potential U 2,3, which will depend on R2 minus R3, for instance. Or over here, between the alpha and the nth particle, we will have an interaction potential U alpha n, which depends on the difference in position between those two particles. This means that in general, we can write that the force between two particles, let's say force between particle alpha and particle beta located at position vector r sub alpha and r sub beta equals minus the gradient of, with respect to the position of the alpha particle, that's vector r sub alpha, of the potential u sub alpha beta, which depends on r sub alpha minus vector r sub beta. So these are these forces. So you can calculate all the forces between all the particles in this way. And because of this now, you could come up with a total potential. The total potential you get simply by summing up all the various different potentials that you have. Right, starting with u12, which depends on the position of the first two particles, and all the other pairs. And you get then that u total is going to be the sum over alpha and over beta greater than alpha, I'll explain why in a minute, of u alpha beta, which depends on r sub alpha minus r sub beta. You might have some external forces too, so I'll add in any potential due to external forces acting on each particle. Okay. So that's the total potential that you'd have to work with. Now the reason why I'm summing over beta greater than alpha is that I want to make sure I don't double count the potentials. So each pair potential here is associated with two particles. U23 is the same thing as U32. And I don't want to double count that. There's only one potential for each pair of particles, not two. And by taking beta always greater than alpha, I ensure that that's the case. Now, because you can find the forces from each of these individual potentials, just as before, by the way, I should remind you that this works in reverse too, that we can get the force on particle beta from particle alpha from the same potential, just by taking the gradient with respect to the second particle. Because of that, we can show, and this is going to be on the homework, that the force on the nth particle, well, that's going to be the force on the nth particle from the first particle, from the second particle, etc. Okay, and each of these is going to be, well, and then in the end, of course, you want to add in the external force. So each of these can be written as a gradient like this. So it'll be minus the gradient, for instance, with respect to the nth particle acting on un1 of r1 minus r2 minus un acting on un2, etc. And then we have the gradient of, with respect to the nth particle, of the external potential, which depends only on the position of the nth particle. And if you sum that up, you get a total force. And we can show, and that's what you're going to do in the homework, that the total force on the nth particle is simply going to equal to minus the gradient with respect to the position of the nth particle of u total, which depends on the position of all the particles. Like that. So you can see that everything looks the same, really, as it did in the case of one particle or one particle pair. We just have extended it to any number of particles. And we can also show, and this is also going to be a homework problem, that if I take changes in the total energy, that is, add up the changes in the kinetic energies of all the particles, plus the total potential, that's equal to now the change in the total kinetic energy, plus the total potential energy, that's going to equal to 0, because all the forces are conservative. Okay. We should also mention that in general, or not in general, but often the potentials will depend not only on the difference in position between the two particles, but actually on just the magnitude of these. So if we have central forces, then the potential associated with two particles really just depends on the magnitude of the difference in position, i.e. only on the distance between the two particles. And that makes things simpler. Now, if you're dealing with a rigid object, it will consist of many particles, just like what we had up here. But in a rigid object, all the particles are the same distance away from each other over time. And because that distance is the same, that means that the interaction potentials are constant as well, and therefore they don't influence the physics. If the potentials don't change over time, well, then the physics stays the same. So that means that the only thing that's going to matter for much of what we do are the external forces and the external potential you might impose on your object. The internal potentials only matter if the object changes orientation, if the object changes its configuration. But if we're dealing with rigid objects, we can largely ignore this, which makes life a lot simpler. And this means that after all, the expressions we had for conservative force due to an external potential is generally going to be most of what we need. This level of complication will, for the most part, not concern us in this course, but I showed it to you anyway, just so you show that everything is consistent and that we can extend the concepts of conservative force to the interaction between many particles.